Welcome to the discussion. Today we're diving into a fascinating paper titled Seismic Prompt Gravity Strain Signals in a Layered Spherical Earth. It explores a novel approach to earthquake early warning. What initially drew you to this research?
The potential for significantly improving earthquake early warning systems. Current methods rely heavily on seismic waves, which can be delayed, especially at greater distances. This research proposes using gravity changes, offering a potentially faster and more reliable signal.
Faster and more reliable? That's a significant claim. How does measuring gravity changes achieve this?
Instead of detecting seismic waves, this method focuses on the subtle changes in gravity caused by an earthquake's rupture. These changes, called prompt gravity strain signals, or PGSSs, propagate at the speed of light.
The speed of light, that's a game changer. But how can we even detect such minute changes in gravity?
That's where advanced gravity strainmeters come in. These highly sensitive instruments can measure the incredibly small spatial gradients of gravity perturbations caused by earthquakes.
Let's clarify something. The paper mentions prompt elasto-gravity signals, or PEGs. How do PGSSs differ?
PEGs also utilize gravity changes, but they suffer from a significant cancellation effect between gravitational and inertial accelerations. This makes them difficult to detect amidst background noise. PGSS, by focusing on the spatial gradient of these perturbations, circumvent this problem, resulting in a clearer signal.
You mentioned gravity strain meters. What types of instruments are we talking about?
Several types are under development, including superconducting gravity gradiometers, torsion bar antennas, and atom interferometric gradiometers. These instruments are incredibly precise, capable of measuring the minuscule changes in gravity that PGSSs represent.
The paper emphasizes the importance of using a layered spherical Earth model. Why is this crucial?
Previous simulations often use simplified half-space models, neglecting the Earth's complex layered structure. This study demonstrates that accurately modeling the Earth's stratification is essential for precise PGSS simulations and interpretation. The Earth's layers significantly affect the waveform and propagation of these signals.
The research also explores the relationship between PGSS and earthquake magnitude. What did they find?
They found a strong correlation between the signal-to-noise ratio of PGSSs and the earthquake's moment magnitude. This suggests that the amplitude of the PGSS signal is directly related to the size of the earthquake. This is a key finding for potential applications in magnitude estimation.
This leads us to the potential application in earthquake early warning systems. How could PGSSs be incorporated?
The speed of PGSS propagation allows for near real-time estimation of earthquake magnitude. By analyzing the PGSS signal, we could potentially issue warnings much faster than current methods, giving people more time to react. The study used the 2011 Tohoku Oki earthquake as a case study to demonstrate this potential.
Can you briefly outline the methodology used in this research?
The researchers used a sophisticated simulation approach based on a multilayered spherical Earth model. They employed the QSSP program to solve the equations of motion and obtain the prompt gravity perturbation. The optimal matched filter technique was then used to detect and retrieve signals from simulated gravity strain meter outputs. Key findings included the significant impact of Earth's structure on PGSS waveforms and the feasibility of near real-time moment magnitude estimation. They also observed SNR saturation at regional distances due to incomplete rupture energy release.
What are the broader implications of this research and what are its limitations?
The research provides valuable insights for future studies on PGSS synthesis and application. It supports the development of gravity strain-based earthquake early warning systems. However, the study relies on simulated data due to the lack of widely deployed gravity strain meters. The point source approximation also introduces some uncertainty.
What are the next steps in this research area?
Validation using real data from operational gravity strain meters is crucial. Further research is needed to refine the models, address the limitations, and explore applications beyond earthquake early warning, such as tsunami early warning.
The paper includes several key equations. Could you highlight their significance?
The equations of motion describe the gravity perturbations caused by an earthquake. The equation defining the prompt gravity gradient tensor is fundamental to understanding the spatial distribution of gravity changes. The equation for prompt gravity strain links the gradient tensor to the measurable strain. Finally, the optimal SNR equation is crucial for assessing the detectability of PGSSs.
Let's talk about the practical challenges of implementing this technology. What hurdles need to be overcome?
The primary challenge is the development and deployment of a global network of highly sensitive and reliable gravity strain meters. These instruments are expensive and require specialized infrastructure. Data processing and analysis also present significant computational challenges. Furthermore, understanding and mitigating the effects of noise from various sources is crucial.
How does this approach compare to existing earthquake early warning systems?
Existing systems primarily rely on the detection of seismic waves, which are slower than the speed of light. This new approach offers the potential for significantly faster warning times, especially for distant locations. However, it's important to note that this is a complementary technology, not a replacement for existing systems. A combined approach utilizing both seismic and gravity data could provide the most comprehensive and robust early warning system.
So in conclusion, this research presents a promising new approach to earthquake early warning with the potential to significantly improve response times and save lives. What are your final thoughts on the implications of this work?
This research opens up exciting possibilities for earthquake monitoring and early warning. While challenges remain, the potential benefits are substantial. The development and deployment of gravity strainmeter networks represent a significant investment, but the potential return in terms of reduced loss of life and property damage is immeasurable.
That was a great discussion. Thank you for sharing your expertise.